Welcome to the fourth episode of the series. In our previous episode, we transformed ordinary sand into an ultra-pure silicon wafer. But a polished wafer, no matter how perfect, still cannot think, calculate, or store information. In this episode, we'll witness one of humanity's greatest engineering achievements: how billions of microscopic transistors are built onto that blank wafer to create the chips that power our modern world. Welcome to a semiconductor fabrication plant, often called a fab. This is one of the cleanest manufacturing environments on Earth. A single dust particle, invisible to our eyes, can be much larger than the tiny features being built on a chip. That's why engineers wear full-body cleanroom suits and every aspect of the environment is carefully controlled. Here, precision begins long before the first transistor is made. A chip isn't carved out of silicon like a sculpture. Instead, it is built one incredibly thin layer at a time. Conductors, insulators, and semiconductor materials are carefully deposited onto the wafer in a precise sequence. Think of it like constructing a skyscraper, except every floor is only a few atoms thick. How do engineers draw circuits that are far too small to see? The answer is light. A special light-sensitive material called photoresist is applied to the wafer. Ultraviolet light then shines through a patterned mask, transferring microscopic designs onto the surface. This process, called photolithography, is like using light as an incredibly precise printing tool. Every layer of a chip begins with a blueprint known as a photomask. Although the mask itself is much larger than the final circuit, it contains the exact pattern needed for that manufacturing step. Just as an architect relies on blueprints to construct a building, semiconductor engineers rely on hundreds of photomasks to build a modern processor. Once the pattern has been transferred, the unwanted material must be removed. This is done through etching, often using highly controlled plasma. The exposed regions are carefully etched away, leaving behind only the structures required for the next stage. It's a process of remarkable precision, where even a tiny error can affect millions of transistors. Layer by layer, the basic building block of every chip begins to emerge: the transistor. By carefully creating the gate, source, drain, and insulating layers, engineers produce a microscopic electronic switch. One transistor may seem insignificant, but billions of these tiny switches working together become the processors that run our phones, computers, and AI systems. Building one transistor is only the beginning. The same sequence of deposition, lithography, etching, and inspection is repeated over and over. A modern chip may require hundreds or even thousands of individual manufacturing operations before it is complete. Precision isn't achieved in one step. It is achieved through consistency across countless steps. Billions of transistors alone cannot perform computations unless they can communicate. That's where multiple layers of microscopic metal interconnects come in. These tiny pathways act like highways inside the chip, carrying electrical signals between different regions. Together, they transform isolated transistors into one coordinated computing system. Before a chip can leave the factory, every individual die on the wafer is tested. Automated probe stations check whether each circuit performs exactly as intended. Some chips pass every test, while others may contain microscopic defects. Only the working dies continue to the next stage, ensuring the reliability we expect from modern electronics. After testing, the wafer is carefully cut into individual pieces using an ultra-precise diamond saw. This process is known as dicing. What was once a single silicon wafer now becomes hundreds of separate silicon dies, each one containing an incredibly complex electronic system built at the nanometer scale. A silicon die is still fragile and cannot be used directly in electronic devices. It must be connected to the outside world, protected from damage, and prepared for installation. Packaging provides electrical connections, mechanical strength, and efficient heat removal. The familiar chip you see on a circuit board is actually the result of this final transformation. Let's take a moment to appreciate the remarkable journey we've followed across this series. It began with ordinary sand, which became purified silicon, then a single crystal, a polished wafer, billions of transistors, and finally a packaged semiconductor chip. Nature provided the raw material. Human curiosity, science, and engineering transformed it into the foundation of the digital age. Modern semiconductor manufacturing pushes technology to its absolute limits. Engineers routinely work with structures only a few nanometers wide, dimensions measured in just a handful of atoms. Every layer must align with astonishing accuracy, and every process must be performed under extraordinary conditions. Building a chip isn't just manufacturing, it's engineering at the atomic scale. At Physical Sciences Consultorium, we believe semiconductor technology is much more than an engineering success story. It represents what humanity can achieve when physics, chemistry, materials science, electronics, and manufacturing come together with a shared purpose. Every chip reminds us that great innovations begin with curiosity, grow through scientific understanding, and become reality through relentless engineering. We've now completed the incredible journey from sand to a finished semiconductor chip. But the story of semiconductors doesn't end here. In the next episode, we'll explore the technologies that may shape the future beyond silicon, from silicon carbide and gallium nitride to graphene, photonic chips, and quantum processors. If you enjoyed this episode, please like, share, and subscribe to Physical Sciences Consultorium, PSC. Your support helps us bring more high-quality science content to curious minds around the world. Until next time, stay curious, keep exploring, and remember, the future is built by those who understand the science behind it. See you in episode 5 of the Semiconductor Age.